Good morning. This is Dr. David A. Padgett. This is World Regional Geography, section 98A. It is Tuesday, no, it's Wednesday, February the 10th, 2021. And so we're going to pick it up where we left off last time. I'm going to share my screen. I'm going to perhaps mention a couple of housekeeping issues, and then we will jump into the lecture for today. And so I'm going to go into student mode here just so that we all see what's going on. Again, for those of you who are tuning in for the first time, welcome. Just FYI, this class is in asynchronous format. And so that means that we will meet live at 9:35 a.m. on Mondays and Wednesdays. However, every lecture will be recorded and will be provided to the class as soon as possible afterwards. And so if you go to the calendar, notice that the lecture recording for Monday is here. And I also send the lecture recording out to everyone's email address so that you'll watch that as soon as possible so that you'll keep up. That's announcement number one. Announcement number two is that uh, there is a writing assignment due on Monday. And so this is the assignment here. And so you will go here, read these instructions carefully. This is a writing assignment. This is your third writing assignment. Most of you have completed writing assignments one and two. This is writing assignment 3. And again, read these instructions carefully. What you see here are the instructions for the writing assignment. And at the other link, you'll see the readings that go along with the assignment. And so these are all the articles that you should peruse as part of the writing assignment. Again, if you have any questions, please get in touch with me. Most of you know that I have a phone number you can call. You can get to this phone anytime, day, night, weekends. I don't care when you call me if you have a question. Again, we don't meet in class face to face, so we must communicate as much as possible so nobody gets lost in the sauce. Okay, we don't want anybody falling behind. Okay, so that is announcement number 2 about your assignment that is due on Monday. What is geography is the name of the assignment. You also have a reading assignment that we're going to get into today. Map interpretation basics. We started the first part of it on Monday. We're going to hopefully wrap that up today. And last but not least, I am announcing 2 weeks in advance that Unit Exam A will be administered on Wednesday, February the 24th. The way that it will probably work is you'll get a multiple choice exam of about 50 questions, all covering Unit A, which is Introduction to Geography. That includes the reading assignments, that includes map interpretation basics. You'll have a GIS assignment next week to complete, and also obviously the geography history timeline, et cetera, et cetera. You'll have, I'm assuming, 4 or 5 days to complete the exam, I think. And then you will, of course, turn it in at the Dropbox and then that will be the end of that. So just look forward to that. February 24th will be the day that the open book exam will be administered. Someone asked me yesterday, is this going to be or is there going to be a review sheet for the exam? Well, no, it's an open book exam. So there's no point in having a exam review for an open book exam, because everything you need you'll have it right there in front of you. No need to memorize anything, but it is best that you read in advance, that you watch these videos in advance, take notes if possible. That way you'll be able to quickly go through the exam without having to cram at the last minute. Okay, so those are the 3 announcements, or 4 announcements. Now it's time for us to get into the map interpretation basics lesson for today. So as you all probably noticed, on Monday, we started off with this document, and on Monday we covered a couple of very basic map interpretation principles. And so we start off looking at map date, and then we talked about directional orientation. We discussed the 3 types of map symbols. And so now we're going to start off today by focusing upon location. Okay, focusing upon location, very important. So as most of you all know, in terms of location, there are a couple of ways that we find our location on Earth. One of them, of course, is relative location, and the other is absolute location. And so absolute location is based upon latitude and longitude. And so we're going to talk about latitude and longitude right now. Okay, so latitude is defined as the arc angle distance north and south of the equator. So the equator is 0 degrees latitude. So we go north to the North Pole. That's north latitude. South 90 degrees to the South Pole is latitude degrees south. So remember last time I mentioned that geography means Earth description, and geometry means to measure the Earth. So when we speak in terms of degrees, if we're at the equator and we go north to 90 degrees, we end up with a right angle, okay? And we know that a right angle is 90 degrees. So that is just kind of give you some idea of where that comes from. So that's latitude. Just to give you some perspective, each whole degree of latitude represents a distance along that circular arc that is between the equator and the North Pole, or the equator and the South Pole. So each degree, say 1 degree of latitude, is actually about 69 miles. Okay, I know that's kind of hard to kind of just try to visualize that. Probably should have a globe over here. I know I have a globe around here somewhere. But so just keep that in mind. Each degree of latitude is about 69 miles. It's actually right over here in the reading, right here. Okay, so just keep that in mind. Now, of course, you should be aware of the low latitudes, the middle latitudes, and the high latitudes. So when you do your reading, just be sure that you know that. Okay, so that's latitude. That's half of how we determine absolute location. Then there's longitude. Longitude is the arc angle distance east and west of the prime meridian. So we know that the equator is 0 degrees latitude. It has a definite definition. It is the circle that represents the plane that bisects the Earth and is perpendicular to the Earth's axis. Okay, so that's what the equator is. We know where that is. It has a quantitative definition. Slice the Earth in half, perpendicular to the axis. You know, the Earth spins, rotates on its axis. That's the equator. But what about 0 degrees longitude? You know, that's a little bit different. Now, yes, the great circle that slices the Earth in half at the prime meridian or 0 degrees longitude, you know, it is a great circle, but there are an infinite number of great circles that slice the Earth in half at the poles. There's an infinite number. So the question is, well, how did we decide which one is 0? You know, now for a while, every society, every nation had its own starting point for longitude. Of course they did. So in China, 0 degrees was in China. In Europe was Great Britain, 0 degrees was there. Everybody had their own individual starting point. But once the world started to become smaller, once we started to engage in international travel and international commerce, having a whole lot of different starting points on the Earth for longitude didn't quite work. So in 1884, 1885, it was decided that the prime meridian would pass through Greenwich, England. Actually, there's an observatory in England, and that's where 0 degrees was decided to be. So it was a human-based decision. It was not based in geometry at all. And so here it is. It was finally in 1884 to adopt the English system. Prime meridian passed through the Greenwich Observatory on the outskirts of London. So that's how we get 0 degrees longitude. I'm going to scale out a bit and go to our map interpretation basics materials for a moment. And we're going to go to this Mercator projection map. And the reason I want to show you this Mercator projection map is because it gives us a relatively easy way to find the prime meridian. And so you might be like, well, how can I know where is it? Where is 0 degrees longitude? I don't know, you might say. Okay, so if we go to, I'm going to zoom in here as closely as I can get. This is not the best. Oh, man. Let's get in here even closer. Those numbers. This is 0 degrees longitude right here. And notice that if we go right here, here's Great Britain, there's England, and that's where 0 degrees longitude is. If you're ever on a map that isn't labeled like this one, and you're looking for longitude, that's where, you're looking for the prime meridian, excuse me, that's where it is, right there. Look, that right there where England is, the one that goes through there, kind of slices part of West Africa off, sort of. I mean, that's the prime meridian if you're ever trying to find it and you can't locate it. And you will need to locate 0 degrees longitude at some point during this class. Okay, so let's get back into the document here. And so again, so the prime meridian is at 0 degrees longitude. And of course, we go 180 degrees east, 180 degrees west. And on the opposite side of the world from the prime meridian is what we call the international date line. That's at 180 degrees longitude. Okay, so when we put the two together, this is where we get absolute location. And so this 39 degrees, 22 minutes, 18 seconds north, 76 degrees, 38 minutes, 5 seconds west is the decimal, is the degrees, minutes, and seconds system. So remember, each whole degree, 39 degrees or 76 degrees, is about 69 miles, okay? Now, if we break that down into, in this case, seconds, there are 60 seconds in every whole degree. So if we divide that into 60 minutes, 69 miles divided by 60 minutes is about a mile, about 1.1 mile, okay? So that's why we take the whole degree and break it down into smaller parts. Now, each one of these minutes is about 1.1 miles. If we break that into 60 seconds, then we get about down to about 100 feet of accuracy using the degrees, minute, second system. Okay, it's just like time. So if you were to ask me right now, you know, what time it is, and I said, well, it's 9 o'clock, you would want me to be a little bit more accurate. How? Well, 9 and what? I'd say, well, it's 9 o'clock and it's actually 9:56. It's 9 and 56 minutes after 9. So that gets us a little better idea what time it really is. And if you really want to be precise, you'd say, well, it's 9:56 and how many seconds? Each minute is divided into 60 seconds. So then that gets us down to a very small unit of time if we want to, depending upon what it is we're trying to measure. You know, if we want to measure how fast somebody runs a 100-meter dash, we certainly would need to measure that in seconds, right? So if you translate that into location, we break 69 miles down to seconds, you know, then we get, well, it's not really this, it's really 100 feet. But 100 feet, that's not really, you know, sometimes we need to be more accurate than 100 feet. And so that's why we use the decimal degree system. So I'm going to go to Google Maps and we're going to do a little exercise with Google Maps. And so we have, so we're starting off with 39 degrees north, 76 degrees west. So let's see, 39, 76. Okay, so Google Maps is really neat in that when we type in 3976, now notice it gives us the decimal degrees and the minute, degrees, minute, seconds system. So let's add something here. Let's go to our, so let me zoom out. Oh, I left something off. Whoa, whoa, whoa. It's N and W. It is in the wrong place. Left off the N and the W. Let's try this again. Okay, so now When I add the N and the W, let's see, where are we? So we are somewhere on the Delmarva, Delaware, Maryland, Virginia Peninsula. So a peninsula is a piece of land that's surrounded on three sides by water. So this is the Delmarva, Delaware, Maryland, Virginia. This tip down here is part of Virginia. So we're on the Delmarva Peninsula somewhere. But is that exactly where this location is? No, it's at 39 degrees, 22 minutes, 76 degrees, 38 minutes. Well, that's 39 degrees, 22 minutes north, 76 degrees, 38 minutes west. So let's add that. Let's get a little bit higher, greater accuracy. So it's 39, 22 north and 76, 38 west. Let's get a little bit more accurate. So now we're down to 1.1 mile, a 1.1 mile level of accuracy. Are we exactly where this point should be? Well, no, because we have to add in the seconds. And so the seconds are 18 seconds north, 5 seconds west. Let's add that. 18 north, 05 west. Now this gets us exactly where we want to be, which is the Boys Latin School of Maryland. It's in Baltimore. Now this is not, I didn't have anything to do with this. I'm from Baltimore, but I didn't have anything to do with developing this lesson. It just so happens that it's at a school in Baltimore, the Boys Latin School of Maryland. This is not my high school. This is a high school. It's a very, it's a private school for the very wealthy, Boys Latin School of Maryland. And so notice that we do have the degrees, minutes, and seconds here, but also underneath it, we have 39.371667 north latitude, and then we have negative 76.63, so on and so forth. Longitude. Now you notice that in the decimal degrees, we don't include the degree symbol. We don't include an N, any of the symbology, except for a minus sign and a period. And that is because if we want to do mathematical computations, we can't do mathematical computations with W's and degrees and all that in our program. And so that's why we use the decimal degrees. The second reason that we use decimal degrees instead of the degrees, minutes, seconds system is for greater accuracy. So if you notice, this is 39.371667. Okay, so that's 3/10, hundredths, thousandths, 10,000ths, 100,000ths, millions. So now we're down to a millionth of that 69 miles. And I'm not going to do the math now, but if you take 69 miles and break it up into a million pieces, you get down to about 4 inches. So when we extend past the whole degree using decimals, now we can get down to a 3 or 4 inch level of accuracy. So for instance, if we were trying to find a state, an entire state, the whole degree might work, might not work, depending upon the size of the state. If we were trying to locate a city, then perhaps if we break it down to 1 mile level of accuracy, then certainly most cities are larger than 1 mile. But if you were trying to find a building on Tennessee State University's campus, you'd need a much higher level of accuracy than 1.1 miles. So in other words, if you had a map and you had a latitude, longitude, absolute location that could be off by a mile, and you entered that into your GPS, and let's say you've never been to TSU before, and a mile away from Fisk University is exactly a mile away from the TSU's gate, right? And let's say you wound up at Fisk, you've never been to Nashville, you might be a little lost, right? But if you get down to 100-foot accuracy, okay, if you're 100 feet away from TSU's student center, the Floyd Payne Campus Center, you should be able to see it from 100 feet away. I mean, it's right there. So that is why that is how we interpret latitude and longitude. You will get a lot more opportunities to work with it once we get into using geographic information systems. And so, like I said, next week you will have an exercise using geographic information systems. And so you will actually get hands-on experience with the with the software. Where did I get that from? And you will be able to get a much better sense of what all these numbers mean when you actually work with the software by hand. Right now, it's probably a little fuzzy. What is Dr. Padgett talking about? I'm confused. But don't worry. Once you start working with the software, it'll make a whole lot more sense. So if you're a little confused right now, that's probably normal. But you have to start somewhere. It's not how you start, it's how you finish that counts, right? Okay, so we've talked about date, location, directional orientation, symbols. Now we're going to talk about the concept of map scale. Okay, so this is going to take us into this document. And we're also perhaps going to get into the textbook a little bit. Let's just start here. Okay, so there are three, the map scale is just the way that we cartographers or any cartographer knows how large objects are on Earth versus the size they are on a map. So any map, or obviously any globe, is a representation of the Earth that is smaller in size than it actually is. I mean, we know how large the Earth is, correct? And so we have globes, but obviously the globe cannot be the same size as the whole Earth, or we would never be able to deal with it, right? And so maps are just pieces of the globe that are at smaller size. But the question is, okay, well, how much smaller are objects on maps than they are in reality? Well, that's what the map scale is for, is to show us the ratio between the size of things on maps and the size of things in real space. So there are three types of map scale. There's the one that you're probably most familiar with is the graphic scale. Let's start there. So the graphic scale you see here, these things on any map. If we go back to Google Maps, you'll notice way down here on the bottom, this little line that says 50 miles. That's the graphic scale. So you know that that distance is about 50 miles. And so you can just kind of say that, well, Baltimore is about 50 miles away, well, from Washington, perhaps, if you use that scale. Notice the scale changes. And that's correct. If you go from the center of Baltimore to the center of Washington, that's about 50 miles roughly, right? So that's the graphic scale. Most of us have used the graphic scale before. Next, there's the representative fraction scale. Okay, so again, this is the ratio between map distances and corresponding Earth distances. So they give you one graphic scale That's 1 to 63,360. So that means that any 1 unit distance on the map is equal to or represents 63,360 of that same distance on Earth. Why is this ratio important? Because there are 63,360 inches in 1 mile. So if you found a map and you found that the representative fraction or for that map is 1 to 63,360, then you would know that 1 inch on that map represents 1 mile in real space. Okay, so if, let's say if you were hiking and you had a map that was a scale of had a map of a scale 1 to 63,360. So you could take a ruler, perhaps. I wish I had a ruler handy. You would take a ruler and you would measure the inches on that map along the trail, and then you would know that if you were to go from one trailhead to the next, how many miles that would be. So if from one trailhead to the next trailhead was three inches along the hiking trail, then you would know, okay, that's 3 miles away. Do we really want to walk 3 miles today? Are we prepared? Maybe we should only go halfway. That'll be 1.5 miles, instead of just not knowing how far you're going and then realizing too late, wow, really wasn't planning on walking 3 miles today. I don't know if we can walk back. I'm tired, right? So you would use the map scale, the representative fraction scale, so that you would know how far you were planning to hike, and then you could decide whether or not you really want to walk that far. Okay. Then, of course, I've already given you the third type of scale, which is the verbal scale, which is when we translate the graphic scale, the representative fraction scale, into a phrase. And that is because, I mean, if you think about it, if I was to tell you before today that a map has a scale of 1 to 63,360, most people wouldn't know what that meant at all. I mean, what? Okay, why is that important? I'm clueless. But then if you say, well, actually, what that means is 1 inch on this map equals 1 mile, then you might say, oh, okay. Now, when you look at the map, you know, okay, 1 inch equals about 1 mile. But so the verbal scale simplifies the representative fraction. So let's say that we had a scale of 1 to 24,000, perhaps. And so let's say we have a scale of 1 to 24,000. And this is a very common scale on a USGS topographic map. Okay, so now again, for most people, if you say, well, I have a map, the scale is 1 to 24,000, most people would say, I don't know what that's about. Yeah, what do you mean by that? But if we were to take this as 1 inch on the map equals 24,000 inches in real space. So if we say that this means 1 inch, this actually means that 1 inch equals 24,000 inches. But still, a distance like 24,000 inches, how far is that? I mean, how many? There's certain distances that we just do not measure in inches, such as miles. You know, before you learn today that there are 63,360 inches in 1 mile, I mean, if I was to ask you, well, how far is it from Tennessee State University's campus to Fisk University's campus, you wouldn't express that in inches. You'd say, oh, it's about 1 mile. But what about 24,000 inches? Oh, how far is that? Well, most people don't deal in inches with that kind of distance, but we could make it a little easier to understand. So if we take that 24,000 inches and divide it by 2,000 feet, what do we get? Excuse me, whoops, sorry. Going too fast. Divided by 12, we get what? 2,000 feet. It's a little bit easier to visualize 2,000 feet versus 24,000 inches. So we would wind up with a new verbal scale that says 1 inch equals, whoops, equals 2,000 feet on that map. So that's our new verbal scale. Now you still might say, I don't know, really, 2,000 feet, I don't know how far that is, but let me give you another. There are 5,280 feet in 1 mile. So given that, you know that, well, 2,000 feet is about a little bit less than a half a mile. That kind of gives you a little bit easier visualization of that distance. So we know about how far a mile is. That's 4 times around a running track. And so if you maybe ran 2 3/4 laps instead of 4 laps, then that's about 2,000 feet, a little less than a half mile. So we should in this class, start to familiarize yourself with map scale. Now, getting into the textbook a little bit, if we go here and we go, okay, come on, textbook. Hopefully this isn't one of those days where the textbook decides to take the day off. Okay, let's see. There we go. And we go here, and then we click here. And this is if you have the book bundle. And then we get here. Now, again, any concept that we want to, the easiest way to find anything in the textbook is to use the search. So if I type scale here, and then we have, go to this part of the book and scroll latitude, longitude. So a lot of these same concepts are in the textbook. And eventually, here we are at map scale. And so again, if you type something into the search bar, it might take you to the chapter. Just keep scrolling until you get to what you're looking for. And so here's scale. It's on page 7 if you have the hard copy book. And so here we have a definition of the various types of representative fraction. So here is a map that is drawn at a scale of 1 to 25,000. So that should tell you that every inch on this map is a little bit more than 2,000 feet, perhaps. Okay, that just kind of gives you an idea. Here, this is a map of downtown Boston, Massachusetts. So a scale of 1 to 25,000 or 1 to 24,000 or 1 to 1,000, those are defined as large scale maps. Now, this might confuse us a little bit. A large scale map, or let me go back, a large scale representative fraction map covers a small area, a relatively small area, such as downtown Boston, Massachusetts. A small scale map, such as the one that's here at 1 to 1 million, now we can see Boston, but that downtown area is now represented by a point symbol. So we talked about point, line, and area symbols. So that little dot now represents Boston. Now we notice that the map also includes a lot of area outside of Boston. The first map that was at a large scale just covered downtown Boston. The small scale map covers Boston and the surrounding area. So smaller scale maps or small scale representative fraction maps cover large areas. And so if I had a map of scale, say 1 to 3 million, that map might cover the entire United States or North America, right? So that might be a little difficult concept to grasp, but you might ask, well, why is this 1 to 25,000 large and the 1 to 1 million small? But what we're talking about here is a ratio, okay? So think about it this way. If you had a pizza and you slice it into 25,000 slices, and you took that same pizza and slice it into 1 million slices, which one of these slices would be larger? Obviously, the one that's at 1 to 25,000, because you only have 25,000 slices, so they would have to be larger. So therefore, that's a large scale. If this fraction is larger, this is actually 1/25,000th versus 1/1,000,000th. So that's why the RF is called the representative fraction. It's actually a fraction. So scale is a concept that it's going to take you a little bit of time to grasp. But again, once we start actually using the GIS software, it'll make a lot more sense when you get into it next week. Just introducing the concept this week. So we have discussed a lot of things. We've talked about location, latitude, longitude, map scale, map symbols, and so on and so forth. Let's move on to the next portion of our map interpretation basics assignment, and that is the map interpretation reading assignment. And so let's look at our various terms. So we've covered direction, absolute location, latitude, longitude. We just talked about scale, the various types of map scale, ISO lines here, topographic map. Now, a choropleth map is a map that uses color area symbols. So remember, there are 3 types of map symbols. There are point, line, and area symbols. A choropleth map primarily uses colors to convey a message to the map reader. We talked about GIS, remote sensing. Oh, generalization. So generalization is when a cartographer leaves certain features off of a map so that it's easier to read. So let's go back to these large scale versus small scale maps. Notice on this large scale map that's zoomed all the way in on downtown Boston, notice we see all these streets. Notice there's all these little streets there. When we zoom out to 1 to 1,000, notice that there are less streets. And then we zoom out to 1 to 250,000, there are no streets. And then absolutely no streets when we zoom all the way out. So the question is, well, why not have all those streets on the smaller scale map? Well, the answer is simple. If we had every little street on this small scale map, the map would look a mess. It would be cluttered. It would be difficult to read, if not impossible to read. So cartographers make conscious decisions about what to include on a map and what not to include on a map. That's called generalization. So a cartographer will purposefully leave certain features off of a map to make it easier to read, especially when we go from a local area map to a much larger area. Some things have to be left off so that the human being can read it. Most humans, most of us can only process about 2 or 3 layers on a map at one time. We get too much on a map, we can't read it. Our minds can't process all those lines or too many symbols and so on and so forth. Okay, so let's now go into this next portion of the assignment. And so this is a nice guide that includes several of the terms that we've discussed already, and a few more: geomorphology, biogeography, physical, so on. There's cartography, GPS, remote sensing, GIS. So you should familiarize yourself with the vocabulary in this document: relative location versus absolute location. So absolute location is when we use latitude and longitude to define a location. Relative location is more qualitative. Relative location would be, say for instance, if you ask somebody, how far is it from TS, where is Fisk located relative to TSU, right? And you ask somebody and they say, oh, it's right down the street. Or they say, oh, it's right around the corner. Or it's over yonder. That's relative location. There's no quantitative definition. It's just a relative location of where one thing is located relative to another, and it can be expressed in very subjective terms. Over yonder, right down the road. And right down the road, for instance, can differ based upon where a person is. So someone in New York City, if you ask them how far is right down the road, that might be 10 blocks. If you ask somebody in Texas how far is right down the road, that might mean 50 miles, okay? Because Texas is much bigger, it's spread out. So we can't really rely upon relative location if we're trying to find exactly where a place is. So that's why we use latitude and longitude. It's a quantitative expression of location. It doesn't matter what language you're speaking. We know where a point is that is at this latitude, longitude, right? There's no question about where this is, okay? It's quantitative. We know where that point is. It's not over there, down the road, around the corner. And so that is the difference between absolute location and relative location. And we've discussed that. Here again is a Mercator projection. I showed you this before. Now on this Mercator projection are some important lines of latitude and longitude. The Mercator projection map is a map projection. So there are a whole lot of different map projections. A projection is a method for making a map. Okay, so you're literally taking the Earth's sphere and projecting it onto a flat piece of paper. So that's why it's called a projection. Okay, so there are different uses for different map projections. The Mercator projection map that you're looking at now is used for navigation. Okay, the Mercator projection is used for navigation because every straight line on this map is a direct compass bearing. Now it's great for navigation, not so great in terms of looking at the sizes of land masses. So for instance, here's Greenland. And we know that Greenland is not larger than the entire continent of Africa, but it looks like that on this map. So the Mercator map does have some distortion in terms of size, but in terms of direction is very useful. And so because the Mercator projection has straight lines representing latitude and longitude, then we can easily locate places on Earth based upon latitude and longitude. And you should familiarize yourselves with these various lines of latitude and longitude. We've already learned about the equator. So there's the equator at 0 degrees latitude. Just make note of where the equator is. The equator does not pass through the United States. It is to the south. Notice here is the prime meridian, 0 degrees longitude. Notice that the prime meridian is nowhere near us. It actually slices through London and then parts of Europe, parts of Africa. That's 0 degrees longitude. So we have to orient ourselves on the Earth's surface, okay? Notice that we have two other lines of latitude that are important, the Tropic of Cancer and the Tropic of Capricorn. So what is important about those two lines of latitude? Well, and here's some more important lines of latitude. Well, we have to go here. The lines of latitude represent parts of the Earth's surface that or points on the Earth's surface that receive the sun's direct rays during the summer and during the winter at various times of year. So if you notice on this diagram, here's the sun, here's the Earth revolving around the sun. As the Earth revolves around the sun, it maintains a tilt all throughout the year. And so this tilt is at 23.5 degrees away from the plane of the ecliptic. I know that's a lot of fancy terminology, but in simple terms, the Earth rotates on its axis, but the Earth's axis is not perpendicular to the plane that slices the sun in half. So the entire time that the Earth revolves around the sun, it's tilted. So what happens is different parts of the Earth get different amounts of direct sunlight at different times of the year. And that's what causes the seasons to change. So for example, let's look at this date, June 20th, 21st in the Northern Hemisphere where we are. There's the sun's direct rays. That's the farthest north the sun's direct rays get, is where the Tropic of Cancer is. So let's go back. So notice the Tropic of Cancer is at 23.5 degrees north latitude. That's the farthest the sun's direct rays strike the Earth during the year. The farthest north, excuse me. The Tropic of Capricorn is the farthest south. So in this region between the tropics, during all times of the year, the sun's direct rays are striking somewhere in here. That's called the tropical region. So when we say a place is tropical, it has a quantitative definition. It's the location on Earth between the Tropic of Cancer and Tropic of Capricorn, where at all times during the year, they receive the sun's direct rays. Notice we don't get the sun's direct rays ever throughout the year. And so therefore, we wind up with the season that's called winter, because during the winter season in the Northern Hemisphere, if you'll notice, there's a deficit of sunlight. It's probably better illustrated on this diagram. And so you notice that on this diagram, which represents the first day of summer in the Northern Hemisphere, you'll notice that the majority of the Northern Hemisphere is in sunlight. If you notice, if you look at the Arctic Circle, which is at 66.5 degrees north, they receive 24 hours of sunlight. That portion of the Earth never falls into the Earth's shadow on that day. Sun's up 24 hours a day. Conversely, the Antarctic Circle during our first day of summer is in complete darkness for 24 hours, and it stays that way until, of course, the opposite happens on our winter solstice. So this diagram represents our first day of winter. Notice the sun's direct rays are at 23.5 degrees south at the Tropic of Capricorn. Notice that the majority of the Northern Hemisphere is in darkness. And so when there is a deficit of sunlight, that results in what we call winter. It gets cold, we get frozen precipitation and snow and ice and all those things that are happening in the Northern Hemisphere right now that some of us like, some of us don't like, so, but again, the seasons change due to this geographic relationship between the Earth and Sun, and we demarcate those points that represent the Sun-Earth angular relationship with these various lines of latitude, Tropic of Cancer, Tropic of Capricorn, and so on and so forth. So your mission, what you should do is recognize that most of the United States, obviously Canada, is not south of the Tropic of Cancer. The only part of the United States that's south of the Tropic of Cancer is Hawaii. The rest of us are in this area that does not receive the sun's direct rays. And later on in the course, you'll see how that affects climate in various parts of Earth. So just familiarize yourself with where these lines of latitude and longitude are, because you will be asked where specific latitude, where specific absolute locations are in North America and really around the world. And you should know where those locations are, whether they're in the United States, not in the United States, in Canada, not in Canada, so on and so forth. Okay. So let's see here. Okay, so I believe that we have, you can do the rest of this reading yourselves. I think we've, the rest of this, I think you can read. And if you have any questions, here's some important places on the map that you should know. So that concludes our discussion on map interpretation. Be sure you watch this video and read these portions of the book, and pay special attention to the vocabulary words that were shared today. Also, just to wrap things up, do not forget that you have this writing assignment due on Monday, February the 15th. And if you have any questions about that, just let me know. And so I'm going to stop recording now. And so that will conclude the recording.